Okay, to talk about motion, we start out with this little video of a toy buggy in motion. We can see it going from left to right across the screen here. It's not too exciting, but I'm going to get a second look at it. We know how to make measurements to describe its motion. As it moves across the screen, I could ask, for example, how far does it go? Which we know means how many meter sticks does it move across your screen. And in the video here, I actually have a tape measure laid out next to it. This yellow strip here is in centimeters. So that's 10, 20, 30, 40, 50 centimeters across. So in order to know how far it moves, I want to compare it to a meter. So I marked out that from here to here is 50 centimeters. It's 0.5 meters. And then what I did was I went frame by frame, and I made a data table of where the buggy is. On the screen it has a X and a Y position, and so I filled in this data table of the X and Y positions at each given time in the video. And we would do this in person on a chalkboard if we were having class that met in person. Start out our study of motion with this type of data table, and then once you have a data table, you may as well graph it. Notice there's a series of red dots corresponding to the red values. Over here, that's the X position. And then there's a series of blue dots that corresponds to the position in the Y. That's because my axis down here is time. So the first thing I want to do right now, before we get any farther into this analysis, is point out one of the things that some students have a little bit of a struggle transitioning to. I think if you're aware of it, it shouldn't be too bad. And that is that we're going to talk about the motion of objects in X, Y, and Z space. Mostly we'll talk about objects moving in one dimension, because moving in 2 and 3 dimensions just gets complicated, especially on a two-dimensional screen like this. But when we analyze motion in the X direction, Y direction, Z direction of space, when we graph them, what goes on the horizontal axis down across the bottom of the screen there is time. So you'll see X or Y or Z on the vertical axis and time on the horizontal axis. That's not actually very confusing, except for the fact that in math class we learn how to graph with X on the horizontal and Y on the vertical. Here we're not trying to compare X to Y, we're trying to compare X to time, and then we're trying to compare Y to time. Once you get a handle on that, this graph is really straightforward. And what exactly is happening in the Y direction? I can look at this Y direction data table, and it looks a lot like not much is happening. These are all 0.5 something meters, and the graph of it is that not much is happening. There's a bunch of dots that, as time goes on, they don't change their value. And that makes sense if you remember back to the video. The buggy moved in the left-right direction. It did not move up-down on our screen. It didn't have any Y motion, really. What's happening in the X direction is what we're seeing with the red dots. For every small amount of time that elapses, the buggy changes its position a small amount. So from this many seconds to this many seconds, to this many seconds, to this many seconds. Each one of them, we see a corresponding change, not only of a little bit of time, but also a little bit of position. A little bit of time changes, a little bit of position changes. A little bit of time, a little bit of position is exactly what the data table looks like, and that corresponds exactly to what we saw in the video. For every frame, it moved a little bit to the right. And the collection of data points, now that I'm looking at them, looks very linear. So if we are noticing that it looks a little bit linear, one of the things that might occur to us to do is to try to get a line of best fit. So I did. I got a line of best fit. You can see it runs right through those points very nicely. I'm going to ignore the blue ones in the Y direction because that was so boring. As the cart moved left to right, it didn't do anything in the Y direction. I'm just going to ignore the Y direction entirely and only analyze what's happening in the left-right direction, that X direction. This line of best fit, mathematicians would describe its equation as y equals mx plus b. And we're going to do the same thing, except we're going to change what a couple of those variables mean. Again, they would call y the vertical axis and x the horizontal axis. So we're going to change those so that our horizontal axis is t in our vertical axis is position in the x direction. So y equals mx plus b becomes x position equals slope times time plus the intercept. And this actually gives me that the slope is 0.1586 meters per second. That means there's units in my slope, which is not something that ever happened to me in math class. We want to give a little bit of thought to what that means, that there's units in my slope. But there are definitely units in my slope here. And my intercept also has units. My intercept is negative 0.06157 meters. What that means is this graph would hit the vertical axes at a value of negative 0.06157 meters, meaning it's actually off screen at 0 seconds. Well, so what that we made a data table and a graph? Is that really that interesting? And the answer is this is useful to us because we can use it to make predictions about things like, well, like where will the cart be at 3.60 seconds or 3.610 seconds. That was not on my data table. Let me back up and show you. I didn't go as far as 3.610 seconds, so I can't just read that off the graph. But because I got an equation off the graph, I can make a prediction. So I take that y equals mx plus b, and I convert it over into a physics description of y equals mx plus b. It becomes position in the x equals the slope m times time plus my intercept. And when I plug some numbers in for that, I have the slope from the previous slide on the graph is 0.1586 meters per second. The time they're asking about is 3.610 seconds. I plug that in here. So the slope times the time plus my intercept, which was the negative 0.06157 meters. And what that gives me is that in the x direction, the position should be 0.510976 meters. And in the y direction, it was 0.05 meters the whole time. It didn't change. So I get this answer that I predict that at 3.610 seconds, the cart will be at x equals 0.51 meters, y equals 0.05 meters. And if that is accurate, then this is useful for physicists to be able to describe the motion of an object in this manner. This is what we want to double check. So I went back in afterwards and made more of the data table after making my prediction. And I added what's happening at about 2.15 seconds, what's happening at about 3.6 seconds. And now we can check to see if where the cart was at 3.6 seconds actually does match our calculated value. We calculated that it was at 0.51 meters, and according to the actual measurements, it's at 0.5177 meters. So that is a useful way to predict the motion of an object. The point of this is that when we're studying motion, when an object is in motion, its position changes as time elapses. And the relationship between the change in position and the change in time is given in the slope of a graph of position versus time. The b, what we typically call the y-intercept, is information about the initial condition of where the object was at the beginning of recording. And the slope tells us something about how the position changes, how far in the x direction this little cart goes for every elapsed moment of time. So what I'd like you to think about is, what would a steeper slope mean? What would it mean if this graph here were much steeper, like say, like this? So give that some thought and then take a look at the next video.